And NEST is a simulation software for large-scale neuronal networks. So where we are thinking about networks, for toy examples, maybe we have a few hundred neurons. The scientifically interesting cases usually start closer to 100,000 neurons. And the largest fully scientifically validated models we have available at the moment are at about 4.5 million neurons. And at the same time, we have taken the technology itself a lot further already. So the largest simulation that we have ever done so far had almost 2 billion neurons. That's about the size of a cat brain. But that was just a technological proof of concept study, so that wasn't a model of a cat brain in that sense. And since then we've taken a step further, so that our technology is also ready for the exascale computers that we are expecting to arrive in the next 2 to 3 years. And then we should be able to push the envelope towards the monkey and eventually the human brain. From a technology side, obviously we still lack a lot of data to really constrain solid models at that complexity. But you can also run it on your own laptop. We even have some people who have gotten it to run on Raspberries. So you can really run it on any scale of computer, from the smallest to the largest around. We have, I think, quite a wide range of potential users who can benefit in different ways. We are currently, with support through an HPP infrastructure voucher, developing Nest Desktop and turning that into a very robust system. This is based on original work at the University of Freiburg, where it has been developed for teaching purposes, and it gives you a graphical user interface for the Nest simulator, so you can construct network models on your screen using your mouse, put neurons in place, or groups of neurons. You can connect them with each other. You can then see how that network responds to input. You can change easily, so just moving some sliders, change parameters in your network and see how the activity in the network changes. And that has proven to be a very useful teaching tool already. And we are right now in the process of making that available through the HPP online services, so that anyone with an HPP account can start playing around. And we believe that that will make a very useful contribution to computational neuroscience education and training. So that's sort of the one end, and the other end are computational neuroscientists attempting to understand the function and the mode of operation of the brain, who are building networks constrained by our knowledge about neuroanatomy, about neurophysiology. And but a challenge that we face is that we have increasing amounts of data about from neuroanatomy. So which parts of the brain are connected with what other parts, how quickly do signals travel, how strong are those connections, but that are a lot of bits and pieces of information to see how they really fit together and make our brain work. We have to integrate all this information into models, and the best way to create such integrated models is really to create them in the computer and simulate them, explore whether the behavior they have is stable. We typically always have quite a number of parameters where we don't have precise values, where we maybe only know, okay, this value is between 10 and 50, but then we can use analytical techniques and simulation techniques to maybe find out, okay, only if we have it between 20 and 25 do we get an activity in this model that is roughly comparable with what we see in the real brain? And that's a type of analysis that we couldn't do without that simulation. Then we have our colleagues in neurorobotics who are building brain models that they use to control increasingly complex robots doing increasingly complex tasks. And they are, for most of their models, also using NEST as an engine. And finally, there is a lot of interest today in modern learning paradigms. So everyone today has heard about big data, machine learning, artificial intelligence, or deep learning. But a challenge with a lot of the current learning algorithms and approaches to learning is that they need tremendous amounts of data to train neuronal networks, and that their ability to generalize is also quite different. Once you want to learn a slightly different task, you again have to have huge amounts of data, spend a lot of time, a lot of energy on learning that. With spiking networks, we hope to get closer to how the brain learns and our ability to learn and generalize from just a small set of examples. And their colleagues are also using NEST for these modern learning to learn paradigms. I mean, one point is just the mystery in itself. How does the brain work? If we look at the sheer energy that powerful computers require today to solve a certain set of tasks and compare that with the quite moderate energy consumption of animal or human brains, we clearly have to learn a lot about how to do certain information processing tasks in an energy efficient way. It is this mystery of how this complex tangle of connections that we have gives rise to our both our behavior of but also then of in the very long run of our own experience of our behavior, our consciousness. But if one looks at how we struggle still today to deal with mental illness, one of the reasons why we struggle so much with treating mental illness efficiently is that we do not fully understand how the brain works. We're quite a bit away from that. If you compare that to the heart, for example, we have a much better understanding of how the heart works, admittedly a much simpler organ, but because we know so very well how the heart works and how every single little part of the heart contributes to the function of the entire heart, we can also intervene in a much more directed fashion. We can even, in detailed computational models that exist, sort of test certain interventions, might they be surgically, might they be pharmacologically, and see whether they would have adverse effects to the working of the heart. And our hope is that by better understanding how the brain functions, we would also be able to provide better guidance for what to do when the brain doesn't function as we should like it to. Well, we have lots coming up. So one is, as I mentioned, this NEST desktop, this graphical user interface that will make NEST much more accessible for the students and beginning computational neuroscientists, and not only make NEST more accessible, but actually neural network modeling as such much more accessible. And Then we are just putting the finishing touches on Nest 3, so the next big release of Nest, where we are making a number of improvements that will allow users to construct complex large-scale models more efficiently. We have a more expressive language to construct our networks, and also done a lot of work behind the scenes to remove certain performance bottlenecks. That is hopefully going to come within the next 3 to 6 months. We can conclude that. Also looking at improved performance for output. If you're simulating very large networks, you have a lot of data that you need to register and store. So Nest 3 is also going to come with significant improvements there. And we are working very intensely with colleagues inside and around, so colleagues working with other tools, on providing a connectivity between Nest and other simulation software, so that we could actually run multiple simulations at the same time, where different simulation softwares describe the brain or parts of the brain at very different levels of resolution, and where we then can have a live coupling between simulators at different scales of description, and thereby really arrive at multi-scale simulations. And I think that will give us very important additional power to do experiments that are very difficult to do so far. In the brain, we have this problem that everything is compressed so much into our skull. So a lot of parts are constantly interacting with each other, and it's very difficult to separate different scales from each other. If you think about the motion of the Earth around the Sun, it doesn't matter where I or you stand here in the room for how the Earth moves around the Sun, because that is just happening on a completely different scale, hundreds of millions times larger than our little movements here on planet Earth. But we don't have this convenient separation in the brain, and therefore we need to look very carefully at how processes at different scales interact, and these multi-scale simulations will make that possible. Nice. Orange. No, that's just our logo color. Let's say reliable, solid, and driven by science.